Enveloped in a thick and highly reflective shroud of clouds, Venus shines with a brilliant luster in the heavens, earning its ancient titles as both the morning and the evening star. Yet, beneath this veil of beauty lurks a world of absolute extremes, defined by crushing atmospheric pressures, scorching temperatures, and an atmosphere saturated with sulfuric acid, a place that seems fundamentally hostile to life as we know it. For decades, however, the scientific community has pondered a profound question: was Venus once a twin to Earth, boasting vast oceans, a temperate climate, and perhaps even the spark of life? What caused its path to diverge so violently? Could remnants of life still persist within the temperate layers of its clouds today? And if so, should we dare to dream of terraforming this hellish world back into a habitable one? Join us as we journey through the historical mysteries and scientific possibilities of Venus, exploring the boundaries of what we know and the bold visions that might one day transform this planet into something extraordinary. This is a long story, so let us begin our exploration of the cosmos, but before we dive in, please remember to support our work by liking and sharing. Venus is frequently described as Earth's sister planet, a comparison rooted in deep physical similarities. At a glance, the fundamental characteristics of Venus mirror our own world in striking ways. It is nearly identical in size to Earth, though slightly smaller in total diameter. This physical kinship results in a surface gravity that is almost as strong as our own, roughly 9/10 of Earth's pull. As a terrestrial, rocky planet, Venus is composed primarily of silicate rocks and metals, featuring a dense metallic core thought to be similar to Earth's, wrapped in a thick silicate mantle. Its surface has been dramatically sculpted by volcanic activity, with vast volcanic plains, mountain ranges, and impact craters providing evidence of a dynamic geological history. As the second planet from the Sun, Venus orbits closer to the center of the solar system than we do. This proximity means that Venus receives nearly double the solar energy that Earth does, a factor that has played a decisive role in its environmental evolution. Despite this, its position within the inner solar system suggests that in its early history, conditions might have been just right for liquid water to exist, a vital prerequisite for life. The defining characteristic of modern Venus is its massive atmosphere, composed almost entirely of carbon dioxide. This composition has triggered a runaway greenhouse effect, where heat is trapped with such efficiency that the surface temperature remains high enough to melt lead. This extreme thermal environment is coupled with an atmospheric pressure nearly 100 times greater than that of Earth's sea level, creating an environment that is profoundly alien. Another critical difference lies in the absence of a significant global magnetic field. While Earth's magnetic shield is generated by the rotation of its liquid outer core, protecting our atmosphere from the erosive power of the solar wind, Venus possesses only a weak induced magnetic field. This lack of a robust magnetic defense, likely linked to its exceptionally slow rotation and internal structure, has left its atmosphere vulnerable to solar radiation, significantly influencing its unique and extreme evolutionary state. The planet's thick cloud cover is its most prominent feature when viewed from afar. These clouds do not glow with their own light but are incredibly efficient at reflecting sunlight. Composed of droplets of sulfuric acid, they scatter about 3/4 of the incoming solar radiation, making Venus the brightest object in our sky after the Sun and the Moon. For centuries, this eternal curtain of clouds kept Venus a mystery. Early astronomers, peering through telescopes, saw only a smooth, featureless brilliance, which led to wild speculations about what lay beneath. Some imagined a lush, tropical world teeming with life, assuming the clouds meant humidity and rain, while others envisioned vast swamps or global oceans hidden under the mist. These visions persisted well into the early 20th century, fueled by the planet's proximity and physical resemblance to Earth. However, the reality revealed by space probes in the mid-20th century was far more stark: an atmosphere of carbon dioxide and clouds of concentrated acid. These sulfuric acid clouds form in the upper atmosphere when sulfur dioxide and water vapor react under the influence of solar ultraviolet light. They create a continuous, impenetrable veil that plays a dual role in the planet's climate. They trap heat with incredible efficiency while simultaneously blocking almost all visible light from reaching the ground, leaving the surface in a dim, perpetual orange-red twilight. This atmospheric density presents a massive challenge for exploration. While radar technology has become our primary tool for seeing through the clouds to map the topography, the environment remains treacherous. High-altitude winds circle the planet at hundreds of kilometers per hour, a phenomenon known as superrotation, meaning the atmosphere completes a full circuit of the planet in just a few Earth days, despite the planet's own sluggish rotation. These winds create dynamic patterns in the clouds that are visible in ultraviolet light, giving the planet its characteristic yellowish-white hue. While the surface today is a parched wasteland, there is compelling evidence that Venus may have once held vast amounts of liquid water. This hypothesis arises from chemical signatures in the atmosphere, specifically the ratio of heavy hydrogen, known as deuterium, to regular hydrogen. In the upper atmosphere, scientists have detected an unusually high concentration of deuterium. Since regular hydrogen is lighter and more easily stripped away by solar radiation and the solar wind, the remaining heavy signature suggests that Venus once possessed a significant reservoir of water that was lost to space over billions of years. Some models suggest that early Venus could have supported shallow oceans covering large areas of its surface. As the planet received more solar radiation than Earth, the heating likely caused surface water to evaporate rapidly, filling the atmosphere with water vapor, a potent greenhouse gas. This created a feedback loop: more heat led to more evaporation, which trapped even more heat, eventually driving the water into the upper atmosphere, where it was broken apart by radiation and lost forever. The geological features of Venus, such as the Tesserae complex, rugged terrains marked by intense folding and faulting, may be the oldest parts of the planet's crust. On Earth, similar deformation is often influenced by the presence of water in the crust, which acts as a lubricant for tectonic movements. If water existed on Venus for hundreds of millions of years, it might have facilitated the formation of these terrains. Future missions aim to analyze the chemical composition of these rocks to find definitive proof of a watery past. Furthermore, the planet is home to massive volcanoes like Maxwell Montes, which stands higher than Mount Everest. The presence of shield volcanoes and volcanic domes suggests a world that was once as internally active as Earth. Some evidence even hints that localized volcanic activity might still be occurring today. While we cannot find fossils on the surface due to the extreme heat and periodic resurfacing events that have paved over the crust with fresh lava, the atmosphere remains a potential archive for ancient biological signatures. The divergence of Earth and Venus is a cautionary tale of planetary evolution. While Earth maintained a stable carbon cycle where carbon is moved between the atmosphere, oceans, and the crust through plate tectonics, Venus lacks such a regulatory mechanism. Without oceans to absorb carbon dioxide and without plate tectonics to bury it, the gas accumulated in the atmosphere unchecked. Earth's magnetic field and its distance from the Sun allowed it to retain its water and develop a biosphere that further stabilized the climate. In contrast, Venus lost its water and its chance at a stable, temperate environment, becoming a victim of its own greenhouse effect. Understanding this transition is not just about exploring a neighbor, it is about understanding the delicate balances that allow a planet to remain habitable. As we look toward future exploration, the lessons of Venus continue to inform our search for life elsewhere in the galaxy and our understanding of our own planet's future. The extreme environment of Venus lacks a moderating biosphere like Earth's, which might have otherwise stabilized its climate. This absence of life is both a consequence of the planet's harsh conditions and a factor that further reinforces its inhabitability. Over vast stretches of time, tiny initial differences between Earth and Venus were amplified, with internal and external factors intertwining to create the stark contrast we see today. However, while the surface remains a scorching and inaccessible wasteland, the high-altitude clouds tell a different story. At an altitude of roughly 50 to 60 kilometers, temperatures range between 30 and 70 degrees Celsius, and the atmospheric pressure is comparable to that found at sea level on Earth. These temperate conditions have led researchers to speculate that despite the highly acidic environment, the upper atmosphere might be capable of hosting microbial life. This hypothesis suggests that specialized microorganisms could survive and even thrive within the cooler cloud layers, provided they evolved mechanisms to withstand the concentrated sulfuric acid droplets. On Earth, we are familiar with acidophiles, microbes that live in extremely acidic environments and derive energy from chemical processes rather than sunlight. Such organisms provide a blueprint for how life might adapt to the rigors of Venus, perhaps by utilizing the abundant sulfur dioxide in the atmosphere as an energy source. If such metabolic processes exist on Venus, microbes might ingest sulfur dioxide and produce byproducts like hydrogen sulfide or elemental sulfur, which could explain some of the anomalous chemical signatures observed in the atmosphere. The mystery deepens with the presence of dark patches visible in ultraviolet images of Venus. These patches strongly absorb ultraviolet light and exhibit unique spectral characteristics that scientists have yet to fully explain. Some researchers propose that these ultraviolet absorbers could be organic in nature or even consist of suspended microbial colonies. Just as microbes on Earth evolved pigments to shield themselves from harmful radiation, similar adaptations could be possible in the high UV environment of the Venusian upper atmosphere. The detection of phosphine in 2020 further fueled this debate. On Earth, phosphine is primarily associated with biological processes, and while its presence on Venus remains controversial and subject to alternative geological or chemical explanations, it highlights the atmosphere's potential as a repository for biological markers. Yet, the challenges remain immense. The acidity of the Venusian clouds far exceeds any environment known to support life on Earth. Sulfuric acid not only destroys biological membranes but also dehydrates organic molecules, making it difficult for cells to maintain structural integrity. Survival would require extraordinary protective mechanisms, such as specialized coatings or the formation of biofilms and spores, similar to how certain earthly microbes survive periods of extreme stress. Furthermore, the scarcity of water is a significant hurdle. While water is essential for life as we understand it, it exists only in trace amounts within the Venusian clouds. Some theorists suggest that microbes might have evolved biochemical pathways to extract water directly from sulfuric acid droplets, a feat mirrored by certain desert-dwelling microbes on Earth that capture moisture from seemingly dry air. Future missions are poised to conduct more detailed explorations of the Venusian atmosphere. Probes, orbiters, and specialized balloon-borne instruments are being designed to sample the cloud layers and search for complex organic molecules, testing whether the ultraviolet absorbers or phosphine signals are truly linked to biological activity. Concepts like the Venus Life Finder aim to use lightweight probes to analyze the isotopic ratios of organic molecules and identify other potential biosignatures. Discovering even the simplest microbes in the clouds of Venus would fundamentally challenge our understanding of the limits of life and extend the boundaries of astrobiology to worlds previously dismissed as entirely hostile. Beyond the search for life, studying the Venusian atmosphere reveals how planets develop conditions that are either favorable or catastrophic for habitability. Comparing Venus to Earth helps us understand the complex interactions between atmospheric chemistry, volcanic activity, and solar radiation, insights that are invaluable as we search for life on Mars, Europa, or Titan. One of the most critical differences between Earth and Venus is the lack of a global magnetic field on the latter. Earth's magnetic field acts as a shield, protecting our atmosphere from the relentless bombardment of the solar wind and cosmic radiation. Without this protection, an atmosphere is slowly eroded, losing key components necessary for life. On Venus, the absence of a significant magnetic shield likely shaped its dry and inhospitable state. While Earth's field is generated by the circulation of liquid iron and nickel in its core, the geodynamo Venus does not possess an equivalent protection, possibly due to its slow rotation or differences in how its core cools. The consequences are profound. Over billions of years, the solar wind has stripped away hydrogen and other light molecules. Observations from missions like the Venus Express have directly confirmed this ongoing atmospheric erosion. On a geological time scale, this loss depleted the planet's water and volatile reserves. During the early solar system, when Venus may have had liquid water and a temperate climate, the lack of a magnetic field made its atmosphere vulnerable. As the sun's energy output increased, ultraviolet radiation broke apart water molecules, allowing the light hydrogen to escape into space. Earth's magnetic field was the primary reason we were able to retain our water, maintaining a stable atmosphere that could support a thriving biosphere. The surface of Venus is also a landscape of geological wonders, featuring vast plains, towering mountains, and complex networks of channels known as canali. Some of these channels, like Baltes Vallis, extend for over 6,000 kilometers longer than the Nile River. On Earth, features of this scale are almost always carved by flowing water, but the extreme heat of modern Venus makes liquid water impossible. This has led to a debate: were these channels carved by low-viscosity lava that flowed like water across the surface, or are they relics of a much older, wetter era? If Venus once had a temperate climate, these valleys and basins might be the dried-up remains of ancient rivers and lakes. Such a period of habitability might have lasted for hundreds of millions of years before the runaway greenhouse effect took hold. To investigate these questions, scientists rely on radar data, such as that provided by the Magellan mission, which revealed the topography hidden beneath the clouds. Detecting salt deposits or minerals associated with water in these regions would provide definitive proof of a watery past. The chemical laboratory of the Venusian atmosphere is a dynamic system shaped by internal volcanic activity and external solar radiation. Sulfuric acid clouds are formed when sulfur dioxide and water vapor react under ultraviolet light. These clouds, which super-rotate the planet in just a few days, create a barrier that is nearly impossible for visible light to penetrate, leaving the surface in a dim, orange glow. The lower atmosphere is so dense and hot that its conditions approach those found inside industrial chemical reactors on Earth, potentially hosting high-pressure chemical reactions that are difficult to replicate in a lab. The 2020 report of phosphine remains a central point of interest, because phosphine is unstable in such an environment. Its presence implies a constant source of replenishment. Whether this source is biological or a result of unknown volcanic or photochemical reactions is one of the great unanswered questions of planetary science. Our understanding of the limits of life is constantly being expanded by extremophiles on Earth. From the scalding waters of hydrothermal vents where bacteria thrive on chemical energy to the acidic Rio Tinto River where microbes metabolize iron and sulfur, life has shown an incredible ability to adapt. Some organisms can withstand radiation levels that would be fatal to humans by efficiently repairing their DNA, while others survive the crushing pressures of the Mariana Trench. These examples suggest that if life ever took hold on Venus, it might have found a way to persist in the unique niches of the upper atmosphere. By identifying the mechanisms that allow extremophiles to survive on Earth, we gain the tools to recognize potential life on Venus or other harsh worlds. The story of Venus is a reminder of how delicate the balance of habitability can be, and how much there is still to learn about our sister planet. Life within the clouds of Venus might depend on highly specialized strategies, potentially utilizing sulfuric acid droplets as microscopic shelters. Given that water is exceedingly rare, hypothetical Venusian organisms might have evolved to use sulfur compounds both as a primary energy source and as the structural foundation for their metabolism. On Earth, we observe certain sulfur-reducing bacteria that transform these compounds into less hazardous substances as part of their metabolic cycle. Similarly, life on Venus could exploit the abundance of sulfur dioxide and other sulfur-bearing molecules through unique chemical pathways to sustain itself. While the dense cloud layers block a significant portion of sunlight, especially at lower altitudes, the upper atmosphere remains sufficiently illuminated to potentially support photosynthetic life. These hypothetical organisms might employ alternative pigments instead of chlorophyll, specialized to capture weak or specific wavelengths of light that manage to penetrate the haze. We see a precedent for this flexibility on Earth in organisms like cyanobacteria, which can shift their light-absorbing pigments based on their environmental conditions. Because the atmosphere is so parched, containing only trace amounts of water vapor, any such life would require an extraordinary efficiency in extracting and preserving moisture. These microbes might have evolved molecular structures or membranes specifically designed to trap water from the surrounding thin air. Furthermore, even if the upper cloud decks are relatively temperate, these organisms would still face the constant risk of drifting downward into the much denser, more lethally hot regions of the atmosphere. To counter this, they might have developed buoyancy regulation mechanisms to maintain their position within the habitable layer, perhaps utilizing microscopic gas vesicles filled with lighter-than-air gases, much like certain aquatic species on Earth use gas bladders to stay afloat. Within these clouds, microbial communities might interact through chemical signaling mediated by sulfur compounds, coordinating survival strategies or sharing resources in a manner reminiscent of the biofilms found in Earth's extreme environments. It is possible that this life originated during the planet's more Earth-like early history, when liquid water and temperate climates were present. As the greenhouse effect spiraled out of control, life may have made a final retreat into the upper atmosphere, turning the thick clouds into a sanctuary from the increasingly uninhabitable surface. If this holds true, Venusian microbes would serve as a profound testament to the resilience and evolutionary continuity of life under extreme pressure. Solar energy, particularly in the form of ultraviolet light, acts as a powerful driver for the intense chemical reactions that define the composition of the Venusian atmosphere. For most known forms of life, ultraviolet radiation is destructive, yet it also has the potential to forge the building blocks of life or support a unique ecological niche. Venus lacks a protective ozone layer, meaning that ultraviolet radiation is far more intense than on Earth, especially within the upper cloud layers. This high-energy radiation can break molecular bonds, creating free radicals that react with other atmospheric components to form complex chemical chains. For life to survive here, it would require robust defenses against ultraviolet damage. On Earth, certain microorganisms produce pigments like carotenoids or melanin, which act as natural sunscreens to prevent damage to their genetic material. Venusian life would likely require even more advanced repair mechanisms to constantly counteract the effects of such persistent bombardment. On the other hand, ultraviolet light also drives the synthesis of organic molecules. By interacting with carbon dioxide and sulfur dioxide, it can generate complex compounds that might serve as raw materials or energy sources for metabolic processes. The high albedo, or reflectivity, of Venus is partially a result of how ultraviolet light interacts with the sulfuric acid droplets in the clouds. These thick clouds reflect a vast majority of incoming sunlight, which actually helps stabilize certain upper regions by preventing them from absorbing too much energy. In the ancient past, when Venus likely possessed water, ultraviolet radiation may have been the primary force driving prebiotic chemistry. However, once the climate collapsed and water was lost, it transformed into a more destructive force, likely playing a role in the formation or depletion of molecules like phosphine. Many exoplanets discovered to date exist in environments of high radiation, particularly those orbiting close to active stars. By studying the role of ultraviolet light in the Venusian atmosphere and the possible adaptations life might use to survive it, we improve our ability to assess the habitability of harsh worlds across the galaxy. This concludes our exploration for today. May your dreams be as vast as the cosmos, and may you have a wonderful day ahead. We look forward to seeing you in the next episode.